Hello, everybody. The item I previewed just minutes ago, we already addressed the issue of for meal as a prefix in nomenclature, and I think we answered her question there. And in this one, there's a few questions here. We have 6 carbons, why we used 5 carbons in reagent. Let's see, this could be forgetting about the carbonyl again. What we have here is 1, 2, 3, 4, 5, 6 carbons. So in this segment down here, there are 6 carbons. And that is because this got attacked by this species here. So the answer to D would be these 6 carbons here. The only way we ever learned, oh boy, I'm gonna lower everything on the screen here. The only way we ever learned to make an anhydride was from an acid halide. That's the piece we have here, and a carboxylate. And that segment here came from here, and this segment down here came from here. And yes, she was correctly concerned here. And I don't like when this happens. I'll explain it to you so that when you see similar typos in the future, that maybe you understand. When I'm drawing a structure and I put a formal charge, and then later on I'm moving molecules around to fit them onto our scheme here, sometimes it forgets the O- was associated with the thing I drew, and then it redoes octets and things, and it thinks it needs to look like this. And I apologize, it's wrong. This H has no business being here. That is a regular carboxylate. In fact, these two are identical. They were supposed to be. So we have the tert-butyl portion over here, CH3 3 times with a C to a CH2 to a carboxylate. There's no H here. So yes, I thank her for pointing that out. Now we do have to get over here for the last portion of her question. What's happening here is, well, let's look. We have a ester. And I'm going to tell you something that it's probably on a video somewhere else, but I'm going to tell you again. When you see an ester, and then you see this leaving group portion of the ester with like an O- as the reactant in a two-step process. Here's the O- with an isopropyl, identical to this O with an isopropyl. When you see that combination of ester and the leaving group of the ester as the base to grab this H here, then you think Claisen condensation every time. Simple Claisen. And HCl is to get this H back on here when we're finished. So I want the simple Claisen product called U right here. And I need to be able to see that. That's a lot better. This becoming the Claisen, which will have, it's not letting me, there. I need to have all of these carbons, but the H missing. Here's product U coming up down here. So you copy everything you see. O isopropyl. The new bond is to the alpha position, and it attacks a second version of the same molecule in a Claisen condensation, and it attacks the carbonyl. Electrons come up and make an O-. They come back and kick off that leaving group, and you end up with everything carbonyl, and to the left, attached down here, carbonyl goes to CH2, goes to tert-butyl group. And just be very clear, there's a carbon right here. CH2. And that is product U. After the first step, you actually have an anion here. And step 2 makes this anion on this position, alpha to both carbonyls, makes it back into a CH as we drew here. These molecules produced in Claisen reactions have that H, which means you should be thinking about taking it off for synthesis purposes. And when I make this anion and I have a molecule that has a double bond here, the reaction that happens, and we'll actually do the mechanism since it's going to happen on your test guaranteed anyway. And we're using OH up there to grab the H, acid base step. I'm going to short form this because writing is getting to be a premium here with space. CO2ET is a good short form. And down here we have carbonyl to R, and R can be neopentyl. And a new bond from this alpha position. And it's going to, oh, we don't have that bond yet. We're just making the anion. There's no new bond. I'm thinking ahead, aren't I? We're about to make a new bond there from this anion. It's going to attack this species that's right at the top of the screen. I'm going to stick figure it. There's a double bond there. It doesn't matter if it's E or Z, but please verify to yourself that this species up here is the same as this. CH3 goes to a C double C, C double C connects to a carbonyl with a CH3. This is a classic 1,4 nucleophile attacking a 1,4 electrophile. The 1,4 name comes from the numbering of the atoms in the mechanism. You attack the position and then call that position number 1. And because the arrows flow all the way up to 4, you call it a 1,4 addition. And you're going to end up with this species here. That's pretty lame. Sorry. Ugh, looks worse. Doesn't sit well with me. CO2ET. And we got a new bond. Very exciting stuff. There's a methyl here. Goes to a C, that goes to double C, goes to an O minus. And her question was, she doesn't see the double bond, and I'm going to answer why she didn't see the double bond right now. Because this is the conjugate base, not of an enol. Although, yeah, you can say it's the conjugate base of an enol. But enols aren't what they start as. They start as the carbonyl. And you're saying, where does that new H come from? And it comes from HOET right here. Solvent being proton source, very common during conjugate additions. Conjugate additions having names like 1,4. And that product that we need to see drawn out on your exam page. Ooh, that's dangerous. That's real dangerous. Don't be losing carbons. There's the TERT. There's CO2ET. Having trouble with that C, clearly. There's your new bond. There's a methyl. Yep, there's no alkene anymore. It got reacted in the 1,4 addition. And just make sure you know this R is not connected to that carbon up there. That's the product I'm looking for. You labeled your R. You could do that on the test. Leave it like this. And we got another question here. Let's do that other question to finish up this little segment. There's our strong base. LDA knows how to do one thing, and let's take an H. In this case, that's the best H, pKa 20. Then that thing's going to attack ethyl acetate. So we're going for Q. You're attacking an ester. This is another Claisen condensation, very timely. It has nothing to do with the attacker. You've generated the enolate from an aldehyde. The fact that it's a Claisen is in the next step. What gets attacked is an ester. Ethyl acetate, I will just try to quickly draw it right here. That's ethyl acetate. It will be attacked by the anion generated right here. Attack, electrons up, electrons back, OET minus off. Then you're going to have a a position alpha to 2 carbonyls. H comes off in the mechanism. You put the H back on with HCl. The answer looks just like a Claisen prediction. You copy the tert-butyl, you copy the carbon that's alpha. Off the carbon that's alpha, you make a new bond to the acetyl group of ethyl acetate. So there's Q. And then Q has this lovely pKa of 10. Means NaOH can grab that easily. And molecule P, oh boy, I hope I have P handy somewhere. I don't even know if I do. I'm probably going to be real sad very soon. Wherefore art thou, P? Oh, P's over here. We have to do everything, guys. That little question mark. Yeah. All right. So Q, we're cool. Don't know what R is until we figure out what P is. Here we're doing LDA and attacking an aldehyde. Hey, that's an aldol. We're going to make molecule O up here. That same anion is going to attack 3-phenylpropanal. 1, 2, 3. Right there. You get an O minus up top, and then HCl gives an OH. And then we're going to dehydrate it there. So O is the aldol reaction product. You copy the tert-butyl. Alpha carbon is going to be attached to something. It's the carbonyl of the green molecule is now an OH. That's why we call this an aldol. We just made an alcohol and aldehyde in the same molecule. And then that's going to condense to make P, which we need next. You're going to lose the alpha position, H again. It'll be a double bond. Go away from the bulky tert-butyl group towards the carbonyl. And there's your P. Q is going to react with molecule P after Q reacts with NaOH. pKa 10. P doesn't have anything approaching a pKa 10. Q does. All right, so anion here is going to attack 1,4. Down here, sorry, new. It's going to go there. Resonate up. I'm going to just, there's the 1,4 addition. I'm going to go straight to molecule S now. Molecule S. NaOH and heat. We better draw R first. We haven't drawn R. Coming up on R right now. The nucleophile is this right here. That nucleophile is attacking there. You're going to get an enolate and then protonate the alpha position right here. So you're going to draw your tert butyl. I don't know why it stopped writing. Because my hand was on the screen. It's another thing I'm starting to do. Okay. This old sigma's still there. The old group is still there. The nucleophile is everything except for that circled H above. Tert butyl attached to a C, which has a new bond here, and we have an aldehyde and an acetyl group sticking off of there. Aldehyde and an acetyl. And that is molecule R, I'm pretty sure. We have all the pieces of the acceptor of the 1,4 addition and the nucleophile. You're saying, where did the H come from here? Well, it came from ethanol. There's an H here. I'm not going to draw it. It's there. Wow. And yeah, NaOH and heat. That's a sneaky one, but there's a big clue at the bottom of the screen, everybody. Big clue. Ring time. Okay, so what's going on here? NaOH can grab one of many H's. It can grab an H here, and if it makes an anion here, it's looking to attack a carbonyl in the same molecule. Will it attack this carbonyl? Answer, no. To do so, the ring size is 1, 2, 3, and then 4. Bad choice. There are no alpha H's here. There's beautiful alpha H's here. They make a perfect ring size 6. 6. So 1, I'm going to number them. 1, 2, 3, 4, 5, 6. We're doing an aldol condensation. How do I know? Well, I'm making an anion that's going to attack an aldehyde or a ketone, in this case, aldehyde 6. When you attack an aldehyde, you do an aldol reaction. The heat does the condensation. So we're going to molecule S. You're not sure what to do. You draw 1, 2, 3, 4, 5, 6 in a ring. Label 1, 2, 3, 4, 5, 6 in the ring. This is the Robinson annulation if you were looking for names for things. You know, I'm not a fan of people's names on there. Carbon 2 was a carbonyl. Carbon 3 had both a formyl. Yeah, get used to these new names. I like them. Formyl and a tert butyl. Everything's becoming green all of a sudden. Carbon 4 had not a benzyl, but a benzyl with an extra C. Did you know that's called homobenzyl? You didn't need to know that. That there's a homobenzyl group. And then 5 has another tert butyl. 5's connected to 6. 6 used to have an OH in the aldol step, which is before the heat was also administered. You get an OH on 6. Aldol condensation with the heat and the base, double bond between 1 and 6. OH gone. There you go. My one looks a little out of position now. There we go. That's molecule S. Wow. So we can finally do molecule G, huh? Well, I'm just gonna help you out a little bit. I'm gonna circle the only new part of the molecule. that wasn't there in S? And how do you get this nucleophile on a position where there used to be a double bond here? I'm helping you out here. You want me to put the numbers up here that correspond to the numbers down there? Why not? Choose the carbonyl. 1 and 6 are here. 1 and 6 and 5 and 4 and 3. And yeah, the only new thing is there, and it attacked the beta position in a 1,4 fashion. So molecule G is everything I just circled there. But it has to be an anion. You could just put the anion on your test. I'd prefer the combination of both this anion and a proton source, comma, HOET is very common. And I don't know, the comma doesn't look so good. There we go. So that's the G combination you need. And a little longish on that segment. And let's just do a preview. I know this series of segments has run out in terms of time of the day, but we have this evening's series as well. Let's look ahead and see where we're going to start this evening. Good. It's a whole new ball game in nomenclature. And I'll see you tonight, later this afternoon, to do that. And take care.